Hello everyone, this is Professor Ma, and this is the introduction on the sections on Lagrange multiplier, uh, which is another applications using the gradient del, partial x, partial y. So the basic Lagrange multiplier is optimization problem, that is find the highest value and lowest values. And the basic setup is this. We have a surface z equal to f of x, y, and we have the domain down here, and let's say it doesn't matter, let's say this is x and that's y, okay, and then we have z, stuff like that. And in the domain, we have a closed loop, and the question is to find the maximum value that this closed loops for the values on the closed loops. Correspondingly, what's happening on the surface is that the closed loop in the domain defines a path, the trails, if you like, on the surface. And so to maximize or minimize the functions over this loop or on the trails corresponds to where is the highest point on the trail and where's the lowest point on the trail. And it's pretty easy to see on the graph. Basically, we are looking for this value, the low point down here, and the high point up here. Okay, and the reason I draw that is that if you ever hike around hills and go on the loops like this, that you know that when you get to the high point is when you're about to go down. In other words, if I was looking at level curves, and let's say these are the level curves of on the surface, and then the point where it's the highest, the level curve and the trail must be tangentials. Okay. The same thing with the minimum points, the lowest point on the curve. If I were to look at the level curves, which will be on here, on this curve right down here, okay, that will be a level curve. And then the lowest point, again, will be the tangent line along the curves and the path coincide. The function below gxy is called the constraint. And this kind of problem we usually call extrema, finding extrema with certain constraint. And here there's only one constraint. And there are also multiple constraints. Okay. Now, if I look at the level curves that I would just draw over, like, for instance, these points, and those are the level curve, and I look at the path, and then we get these situations. These are the level curve, z level curve, z level curve. So if I'm looking from a drone flying on top, take a picture downward, and there you are at the high point of the trail. And it must be the trail path start going down. It's not going to pass through the level curve, no. Okay, so not like that. So the drone knows that you are on top when the tangent line to the level curves is the same as the tangent line for the constraint. Which means the following, means they have the same gradient. So they have the gradient pointing in the same directions. In other words, the gradient, one gradient is the multiple of the other gradient. So in terms of partial derivatives, then the gradient means the partial derivative of x must be the same up to a lambda multiple. Oh, again, the lambda is a fixed constant, so that lambda must work for both partial x, partial y. So in this setup, we introduce an extra variable lambda. So to solve for xy, so given equations in xy and constrain xy, we set up this system equation and we solve xy. The lambda is called a multiplier. It shows up in algebra often. That is, you solve some sort of situations with it comes out with constant multiple, then you have to figure out the constant multiple. So here's an example. Okay. What's f of xy equal xy? If you think about it, that's a saddle. What's x squared plus y squared minus 2 equals 0? Move the 2 to the other side. This is a circle. Okay. So we'll have to then solve the equations, partial derivative. We go to multiple of the other, and we get that. And when we solve that equation, and how do we solve this equation in general? We solve the lambda, and then try to plug the lambda a into the other equations. Okay. So this is how this one is solved. The lambda to y equal to 2x over y, then you take 2x over y. This came from here, then you take over here and plug into this lambda. And then you got two equations with x's and y's, and then you solve those equations for x and y's. So I won't bore you with the algebra. A word of you don't have to really solve for lambda. If you can do this substitution to get rid of one variable, you can solve this lambda with the equation with x and lambda. You solve x and lambda. Okay, and so the rest is algebra. You can check it. Okay, I'll leave up to you to check the algebra. Okay, and then you get two pair of solutions, plus minus 1. Then you find the corresponding y values here. Y to x, and so you can find out that therefore these are the 2 points on the circle. Oops. These are the 2 locations on the circle where the high and low points are. So let me move it back here. Then here is the pictures. So 1, 1 is a maximum, minus 1, 1, 1, minus 1 is a maximum. And then at the other 2 corners of the square, those are the minimal. And these are the pictures for them. Okay, the circle is the domain. This is the circle x squared plus y squared equal to 2. And then this is surface z equal to x squared. And the path, and we have the 2 minimum points and 2 high points. And this Lagrange multiplier methods works for any dimensions. Okay. So in general, you wind up with these equations in 3 variables, and you take the partial derivative. The gradient has to be the multiple of the other one, so the partial x has to be the multiple, partial y has to be multiples, z has to be multiple, plus this original constraint, x, y, z must satisfy g, x, y, z equals 0. The bottom. This is the list of equations, and you try to solve it. Okay. In general, might be easy. Yeah, what kind of things can happen? So we are going to do the homework will just be some of the basics algebra. There will be no fancy algebras on tests. Okay, here's water problems, and we find the largest volume possible. We with a fixed amount of area, surface area. Well, the surface area is the constraint. The formula we want to maximize is x times y times z, the volume. So this is the surface area. Okay, and we're given a fixed constant. So when we take partial, the constant doesn't mean anything. It's going to become 0. Then we set up a constraint equations, system equations for the constraint, for the gradients. Then solve them. And so in this one, we solve for z. So we solve for z, then we get formula in x lambda y. And then we proceed with another and so I leave the algebra to you. There's nothing really, all basic algebra. And that's it. That's basically Lagrange multipliers. See you next time. Bye-bye. Stop share. Bye-bye.